Next, we're going to talk about an ACF now for an ARMA model. Obviously, we've talked about an ACF for both the AR component of a model and the MA component of the model, but we do need to take some time to put the two components together. Now, the reason why, in terms of the big picture, the reason why we're doing all this is so that we can understand what the ACF looks like for a variety of different models. And we can compare these ACFs to what is actually estimated through an observed time series. Values and patterns for the, let's say, the true ACF compared to the estimated ACF. Values and patterns that match between particular models with that estimated then will lead us to using that kind of a particular model for the actual time series itself. That again is the big picture, why we take so much time and why it's so important to fully understand this autocorrelation function relative to various models. So to begin here, we're going to take a look at the ACF for a moving average order Q model. We've seen previously what it would be for Q equal 1, but what about in the more general sense? So here's what our model looks like once again. X of t is equal to, we have the AR operator, which written out is 1 plus theta 1b plus theta 2b squared, all the way down to the qth term in the sum. Now, another little bit more compact way that we could write all this is as follows. Take the sum from j equals 0 to q, theta sub j, b raised to the j power wt, where we say that theta 0 is equal to 1. So we include, this extra theta in there, mainly for convenience, notational convenience, let's say. So with our particular time series here, our autocorrelation function ends up just again simplifying down to the expected value of xt times x sub t plus h. And to find then this expected value, let's plug in what xt is here and also what xt plus h is as well. Then we can multiply out the corresponding terms. The easiest way to see this is suppose q is equal to 1, what do you get? Suppose q is equal to 2, what do you get? You start seeing patterns occur, so that in the most general case we have a double summation, I equals 0 to q. That's the first summation. Second summation, j equals 0 to q, theta sub I times theta sub j. We have two w's here with time indices of t minus I and t plus h minus j. We can bring the expectation through the sum, and also those thetas are constant, so we can further bring that expectation through, and this is what we get now. Now, with respect to this expectation, the only thing that we are concerned about in terms of that are non-zero values is when these subscripts match up. We've seen something like this before. And so, again, you could look at specific cases. Let's say q equal 1, q equal 2. You can see the patterns that form. And then when these subscripts match up, we get a sigma squared w. And we're left with, in terms of the summation now, the sum from I equals 0 to q minus h, theta sub I, times theta sub I plus h. Okay. So what that means then for us is that our autocovariance function is written like this. And this goes up to a lag of q. Because once we get past a lag of q, let's say q plus 1, we are no longer going to have these subscripts match up for the w's. And so when h is greater than q, we get an autocovariance function of 0. And this is very, very interesting, that essentially what happens is that using a term that we often use in time series analysis, the autocovariance function cuts off at lag q. it becomes 0 after that. So what that means then for us is if you were to, let's say, observe some time series data, and with this time series data you do a plot of the estimated ACF, and if you see some large autocorrelations at, let's say, lag 1, lag 2, maybe even lag 3, and then all of a sudden the autocorrelations are very, very close to 0, then that tells you that a moving average 3 model, because we had 3 autocorrelations that were non-zero, a moving average 3 model may be appropriate for your observed data. Okay. So at h equals 0, what happens? Of course, then this becomes a 0 there. So now we have some thetas that are squared. So there is my my variance at lag 0, or my autocovariance function at 0, at lag 0, which is the variance. And so when I can find now my autocorrelation function, I just take this lag 0, put that down there, and then for lag h equal 1, 2, and so on, I'm going to get what's in the numerator. And there's my autocorrelation function. Now, one could do a similar derivation as well, using the result that we had from a linear process earlier. So in this next set of bullets here, I just show you, okay, well, what happens when we have a moving average 1? In terms of, we've seen this before, but just not necessarily written in terms of this general form here. So when lag is equal to 0, I'm sorry, when the lag is equal to 0, we have gamma 0 of let's see here, we have theta 0 squared plus theta 1 squared. Also, we're going to have a sigma squared w out there. We know this theta 0 is equal to 1, and so this is how we get this result there. Similarly, you can see on your own for lag 1, sigma squared times theta 1, and of course we have the autocovariance function equal to 0 for h greater than 1. So then here's what our autocorrelation function looks like. Again, we've seen this in the past. Here's what a plot of the autocorrelation function looks like as well. You know, the main thing to look at is, notice we have no values, all the values are 0 after lag 1. So then what happens for an MA2? I'll let you look through some of the details here on your own. The main thing to see here is that for lag 0 through 2, we have non-zero autocovariance values. For greater than lag 2, we do have a 0 autocovariance value. Okay. So let's take a closer look then at a more complicated model, the ACF for an ARMA PQ. So the autoregressive component has P parameters. The moving average component has Q parameters. So the first thing that you need to do in these kinds of settings is to rewrite the model as an infinite order moving average. So here's our original model here. We can take the phi sub b, bring it over to the right hand side, and then basically what we're going to do is equate the theta over b divided by the phi over b with psi of b, where psi of b is this infinite order sum that we basically have. Now we can rewrite then this particular model in terms of the size, similar to what we saw with the moving average Q model, where now we have x of t is equal to I equals 0 to infinity, psi sub I, b raised to the ith power, w sub t, where psi sub 0 is equal to 1. And again, we just do this for convenience. Then to find then the autocovariance function for this particular model, gamma of h, we put in what x of t is and what x of t plus h is, written in terms of our infinite order moving average. Again, start multiplying stuff out. Work with a special case if you need to, so that you can see how This all simplifies, and we get this double summation similar to what we had before with just a moving average Q. The key difference is now we have these psi parameters there. We can move that expectation through the sum, and this is what we get next. Then, again, only when the subscripts match up on the W's are we concerned with, because otherwise, because of independence amongst the W's, we get a value of 0 for the different for the expectation. So when the subscripts match up, we have basically an expected value of WT squared essentially, which is equal to sigma squared W. Our summations now become just one summation, I equals 0 to infinity of psi sub I and psi sub I plus 1. I'm sorry, plus H. So this autocovariance function is written in terms of these psi's. We would like it to actually be written in terms of the phis and the thetas. And I'll have an example shortly that shows how to go about doing that. So another way to find this autocovariance function that's kind of interesting is to first rewrite the model so that we have x of t on the left side and everything else on the right side, as I did here. And then the autocovariance function could be found as follows. Autocovariance function is covariance of x of t plus h and x of t. So here's x of t plus h written in terms of like the model that we have up here, but now I have a lag h. That quantity times x of t. That's my covariance again, because expected value of x of t in this kind of a model is equal to 0. Also, then, what we can do is move this x of t into this sum and into this sum. And so let's say this, we'll call that step 2. Step 2, that's exactly what I do. I can then move the expectation through the sum and also the constants, so that's step 3. And then look what I get here for step 4. What this basically represents right here is an autocovariance. So it's my autocovariance function at lag h minus j, as you see there. Also, I can rewrite my model in terms of what, again, x of t represents if I were to write it in terms of an infinite order moving average, and that's what I did in this particular step 4 as well. So then our autocovariance function can be represented like this. The sum from j equal 1 to p of phi sub j gamma of h minus j plus sigma squared w, the sum j equal h to q of theta j psi sub j minus h. Now, I did a little bit of simplification here because, again, remember when we have the expected values of these two w's, the only time that we're the only time that's non-zero is when the subscripts match up. Okay, so that's our autocovariance function. And if you look at it a little bit further, you can see that I only have to be concerned about this portion here when h is less than this particular value, the max of p and q plus 1. And then once you get beyond this maximum, then my autocovariance function just simplifies down to that first part. If I were to divide this gamma h by gamma of 0, then I get my autocorrelation function. And so you can see almost, I don't want to call it a recursive relationship here, but you can see this provides kind of an interesting relationship between different autocovariances and autocorrelations with the autocovariance and correlation that we're interested in. So let's apply some of these methods to an ARMA 1-1. So here's my ARMA 1-1. I have these two. I have one term for the AR part. I have one term for the moving average part. I can rewrite my model so that I have the moving average operator divided by the autoregressive operator, and I'm going to set this equal to this psi of b, this infinite order, this infinite sum, you could say, that leads to an infinite order moving average. And so then when I do set this equal to one another, well, what does this mean for us? Well, then I can take this 1 minus phi 1 times b, multiply it by psi of b, and look what I get here. I get this equality. Then what I would like to do is find what these psi should be in terms of the phis and also the thetas. And the way that we're going to do this is very much like what we've done before for simpler models, is that we're going to match up powers of b to find what the corresponding psi's would be, as in BE. So let's first take 1 times this infinite linear combination. This is what I get there. Then I'm going to take negative phi 1b times this infinite linear combination. This is what I get there. Set that equal to 1 plus theta 1 times b. So now let's equate powers. So let's say we could start off with b to the 0 power. That will correspond to this one, and so we have equality. That's not much fun. So let's go to b raised to the 1 power. Let me do a little bit of erasing here too, so I can mark this up better. So b raised to the 1 power, we got psi sub 1 times b minus phi 1 times b is equal to theta 1 times b. So that means theta 1 is equal to psi 1 minus phi 1. What is psi 1? Well, it's theta 1 plus phi 1. Next, let's go to b squared. We have a psi 2 times b squared minus a phi 1 times psi 1 times b squared. I have no b squared over there, so I set 0 is equal to psi 2 minus phi 1 times psi 1. Okay, what I want to do is find psi 2. So what I can do now is, let's say, move this over to the other side. And actually, I kind of reversed it here in how I wrote it out. So we have the phi 1 times psi 1, which we had just found previously. For b cubed, we have a similar thing happening here. Psi 3 is equal to phi 1 squared times theta 1 plus phi 1. Notice the pattern that we're starting to see here with these terms. So to find then the corresponding autocovariances, I can rewrite my autocovariance function as sigma squared times the sum I equals 0 to infinity of psi I times psi I plus h, using a result that we've had previously. And what I can do then for gamma 0, just plug in h equals 0. Look what I get, sigma squared w times that sum of sigma I squared. Plug in what these sigma i's are. I'm sorry, not sigma i's, these psi i's are, in terms of what I just found. And do a little bit of simplification. I'm not going to go through all the steps. And this is what we get for the autocovariance function at lag 0. At lag 1, you can do the same thing. Notice now I have two psi's always multiplied by each other, and I get an autocovariance function that looks like this for lag 1. We went through this stuff, a lot of this stuff before. It's a lot of algebra, and I'm not going to go through all the details as I maybe had done in the past. Okay, now using this alternative way to approach then how to find this autocovariance, what we can do again is rewrite our model. So we have x of t just on the left side, and then we have everything else on the right side. Based upon what we saw previously for this representation, we would have p here, we would have q there. I can write out my autocovariance function in this particular form. And since p is equal to 1, this first term actually becomes really simple. It's just phi1 times gamma of h minus 1. Also, this second term is relatively simple as well. Sigma squared w times the sum j equal h to 1. Notice how the role that h is going to play here. H isn't going, since h can be greater than 1. This term here, when h is greater than 1, is going to be 0 because it's an empty sum, using standard definition of what summations are. And we have a theta j psi sub j minus h. Okay, so if h was equal to 0, we have gamma of 0 is equal to phi1 times gamma of negative 1. Now remember, with our models, this is equivalent to gamma 1 because it doesn't matter if you're shifting up or you're shifting down in terms of our lag. We have a sigma squared times, again, h is equal to 0, so we go j equals 0 to 1. We have the theta 0, psi 0. Each of these components are equal to 1. Then we have a theta 1 times psi 1 there. Again, a little bit of a simplifications then. You come down to this end result. Notice it's written in terms of gamma 1. So what is gamma 1? Well, again, we could use our expression here. We get phi1 times gamma 0 now. So we have h, which is 1, 1 minus j. Our summation is from j equal 1 to 1. So we have 1 there for j. So 1 minus 1 is 0. Plus, now, sigma squared w, theta 1 times psi 0. Psi 0 is equal to 1. So, what we have here is two equations and two unknowns, you could say. We want gamma 1. We want gamma 0 as well. So what we can do is take then, we have the gamma 0. We're going to plug in what gamma 1 is right into there, do a little bit of simplifications, and we get this result for our gamma 0, which, if I come back up, matches what we had before. Now that I have gamma 0, what I can do is simply plug in that gamma 0 into there, do some more algebra, and here's what we get for gamma of 1. Now to find gamma 2, gamma 3, gamma 4, we only have to be concerned about the first part of our summation, because that other part disappears because h is greater than the max of h is greater than or equal to 2. And look what happens here. Gamma of 2 is equal to phi1 times gamma 1. Gamma 3 is equal to phi1 times gamma 2, just simply using that part of our expression. And thus then we get a general expression then for what our autocovariance looks like. Take that divided by gamma 0, then we get our autocorrelation function. So what we see here overall is that, unlike what we saw for the ACF for a moving average Q, this autocorrelation is not equal to 0 after a particular lag. So in terms of the big picture here, why do we want to know the ACF for an ARMA 1-1? Well, again, if an estimated ACF of a time series dataset exhibits similar characteristics to what we have here for the autocorrelation, then we might think that the time series dataset can be modeled as an ARMA 1-1. So we can also look at the ACF of an ARP model as well. So in this particular setting, I'm not going to go through all the details here. Gamma 0 can be written in terms of this second way that we looked at to find then the autocovariance. In the end, this part right here doesn't play much of a role, ends up being sigma squared W. When h is greater than or equal to 1, this extra part here drops off, and we're left with just this here. So if P is equal to 1, we can then go ahead, use this expression to find the autocovariance, and what we end up with is we have an autocovariance of lag 0 of sigma squared W over 1 minus phi 1 squared. Here's at gamma of 1, gamma of 2, and so on. And what ends up happening, we've seen this before, the ACF is phi 1 raised to the h power. And a key thing here to realize is that because of the constraints on phi 1, we know that this ACF, the autocorrelations, are going to start tailing off to 0 because of possible values for phi 1, and we're raising it to the h power. So like 0.5 raised to the 1 power is 0.5, 0.5 raised to the 2 power is 0.25, 0.5 raised to the 3 power is 0.125, and you can see how that autocorrelation is going to 0. Very often we will refer to this as tailing off to 0 in time series context. And so when we see something like this, then that says, well, maybe an autoregressive 1 model might be appropriate. When we have P equal 2, we can again use our expression, that second expression for what the autocovariance function is, to find a convenient representation for the autocovariance and then also for the autocorrelation as well. And what we end up with, which is kind of interesting, you get phi 1 times the autocorrelation for lag h minus 1 and phi 2 times the autocorrelation at lag h minus 2. You can go through the details of, well, what happens if h is equal to 1, what happens if h is equal to 2, and get the corresponding representations for those autocorrelations. You can keep on going for lag 3 and 4 and so on, and what you're going to see once again is that that autocorrelation function is going to be tailing off to 0. It's going to get closer and closer to 0 as the number of lags increases. So unfortunately for the ACF for an autocorrelation function, we don't have this cutting off to 0. So it's going to be very difficult to use the autocorrelation function to figure out what will be the appropriate order or appropriate value for P. Instead, what we will use, learn about shortly, we're going to use a different kind of function called the partial autocorrelation function, which will have this cutting off to 0 at a particular lag quality, similar to what the moving average did with the autocorrelation function. This other partial autocorrelation function will be very helpful for us. So here's a table of ACFs then for common ARMA models. Please take a look at this on your own. Also, when you look at this, this is a common thing that you will see actually displayed in a textbook on time series analysis. Please remember that not all textbooks use exactly the same notation. So the way that they represent the way that they display the autocorrelation function might be different than the way that I do here. Note that this way that I'm showing it is the way that Shumway and Stouffer's book does. So in summary then, and this is very important, what we're going to see with these ACFs, if an ARP model is appropriate, then you're going to see the ACF tail off to 0. If a moving average Q model is appropriate, that ACF is going to cut off to 0 after lag Q. And if an ARMA PQ model is appropriate, because of that moving average part right there, we're going to have some, relative to 0, we're going to have some autocorrelations in terms of absolute value that are going to be away from 0. And then because of the autoregressive part, then the autocorrelations are going to be tailing off after lag Q. So here's also a display what the AR1 model ACF looks like. And just to show you what can happen then, suppose I actually use the ARIMA.sim function to actually simulate data from this particular model. 1,000 observations, this is what it looks like. And if I were to actually calculate then the estimated ACF, you can see it follows the exact same pattern. Okay. Take a look at the ARMA ACF function, which we've seen before, to see what other ACF plots will look like for different values of phi 1. Combine it with cases where you have theta 1, maybe a theta 2, a phi 2, and so on. So then that concludes then this discussion of ACFs for an ARMA model.